Good evening, and thank you for joining our last 6 at 6 of the 23-24 season. I'm Shauna Riley from the Scripps Howard Center at Northern Kentucky University, and it is my pleasure to introduce our speaker tonight, Mahdi Yazdanpour. He is from the Department of Physics, Geology, and Engineering Technology. And yes, that's a lot of words. So thank you for all of you who are joining us today in person and online. We have had a lot of folks stuck in traffic tonight. There seems to be lots of road accidents on 75 and 275, so we really appreciate those of you who battled the traffic to join us. For those of you who are online, you can use the chat function to ask questions. Sorry, the question and answer function on the Zoom to ask questions, and we will ask Dr. Yazdanpour during the question and answer section. And with that, I'd like to turn it over to Mind Over Matter.
All right, thank you so much for the introduction. Good afternoon, everyone. I hope you had a wonderful day, and thank you so much for attending this session. I'm Dr. Yazdanpour. I'm Assistant Professor and Program Coordinator of Mechatronics Engineering Technology at NKU. And today, I would like to talk about our recent project, Brain-Controlled Robotic Arm. So I'm very interested in multidisciplinary research projects, probably because of my diverse background. So you can see I received my Ph.D. in electrical engineering, my master's degree in industrial engineering, and my bachelor degree in computer engineering. So many different engineering fields, which I think was a good decision. It helps me to see engineering problems from different perspectives. And I'm very interested in multidisciplinary research projects, combination of engineering, robotics, science, neuroscience, and this type of things. So I'm assistant professor at NKU. I joined NKU in 2019, and before that, I was a PhD candidate and also instructor at Oklahoma State University. I'm coming from industry. I have worked in industry for more than 10 years, and I always would like to share real-world experience and practical things with my students. Okay, my research interests. I'm interested in intelligent mechatronic systems, medical robotics specifically, human-robot interaction, brain-computer interface, or brain-machine interface, brain-controlled systems, and computer and machine vision. Today, specifically, I'm going to talk about brain-computer interface and how we can use it to control a robotic system, electromechanical system. So if you like, you can scan this QR code and you have access to these slides. And hopefully you can see it. So let me zoom in. It works? Great. Okay, question. I said mechatronics. So it's a new field. So do you know what is mechatronics engineering?
No.
You should know.
You should
because you have this class system as well.
I don't know, I can interact today, but yeah, it's a combination of control systems, computer systems, mechanical, and engineering, electrical engineering.
Perfect. So Faz is in my class, mechatronics systems class this semester. Thank you, Fazim. Question, this image is completely AI generated. And I asked AI model to generate a picture for me to show combination of engineering and science, specifically focused on mechatronics. It's a very nice picture. And I was wondering why we have one apple here. And I asked, okay, very nice. Why did you add that apple in the middle of that image? And this is exactly response from Copilot. So I love AI, so here's good I love it. Okay, let's go back to our initial question. What is mechatronics? So in a simple word, is combination of mechanical, electrical, and computer engineering. This word comes from combination of mechanical and electronics. I think as if for the first time, Mr. Mori, who was working in Yaskawa company in Japan, actually released this technical term in 1969. So this company was working to integrate electrical features with some manufacturing mechanical equipment. So Mr. Mori was looking for a right term to show the combination of mechanical and electronic things. And here we have mechatronics. So for the first time in 1969. So this one is actually the better definition. What is mechatronics? It's a multidisciplinary field, synergistic integration of mechanical engineering, electronics, computer engineering, and computer science, and control engineering. It means you can design, simulate, develop, and develop different electromechanical systems and then add intelligence to them. So imagine a computer-based electromechanical device, and you can use a control unit to control it. So this is a nice definition for this technical term. So you can see here, combination of control systems, computers, mechanical systems, and electronic systems. And this is my favorite image. Imagine you have so many electromechanical devices in different fields, and you can add intelligence to these systems. You can make them smart. You can enhance functionality and productivity of these devices. Another image created by AI, I asked him to, combine intelligence with electromechanical devices in different fields. And I think this one was the nicest picture I saw today. And you can see different applications. And today we are going to focus on smart medical robotic systems. Okay, what was the problem? The Amputee Coalition of America estimates that we have nearly 2 million amputees in this country. Each year, we have 185,000 new cases. Imagine, it's a large number. One study from NIH states that we have these numbers. 84% of people with lower limb amputation and 56% of people with upper limb amputation use different types of prosthetics. As you can see here, traditional prosthetic devices, like these devices, they need body power, and they have so many different types of limitations. We have some bionic arms. They are artificial limbs actually designed which use specific sensors to capture electrical impulses from muscles. And then using those sensors, you can control different parts of the arm, fingers, for example. Bionic arms use electromyography or EMG sensors as an interface. So they can use those sensors to capture those pulses from muscles. Usually we have two types of EMG sensors. We have surface EMG or SEMG, as you can see in the left side. They are not very accurate. So EMG-based interfaces are not very robust and accurate. In the right side, we have intramuscular EMG sensors. The problem is if patient wants to use them, they need surgical placement. They need a medical procedure because you need to actually place them under the skin. So Bionic arms, which use EMG sensors, are very expensive. I will show you a table with actually current prices. They have limited precision. In different situations, imagine muscle fatigue, imagine a signal crosstalk. They are not very accurate in this type of situations. They are very sensitive. They are not customized. Most of the bionic arms you can find on the market, you need to order, for example, a small, medium, or large. They are not customizable. And if they are in this category, they might be invasive. So they need medical procedure. So here in this table, you can see the available bionic arms, which all of them are EMG based. They use myoelectric sensors. To the best of our knowledge, there is no commercially available EEG based prosthetic arm on the market. You can find some research papers, some articles, but you cannot find something commercially available that you can purchase. So you can see range of the price, minimum something close to $8,000, and it can go up to $100,000. These three, Esper Bionics from Esper Hand Company, Hero Arm from Open Bionics, and TrueLimb from Unlimited Tomorrow. These last three are very famous and they are available, so you can purchase a bionic arm from these companies. First one, Esper Bionics, very nice and innovative bionic arm, as you can see here. Combination of different materials. They use 24 EMG sensors to capture electrical pulses from muscles. They have just two sizes, small and large, and as you can see, weight 0.837 pounds or around 380 grams, and price $2,000. It's a very nice bionic arm, but you can see price. So $2,000 plus, of course, hidden fees. Hero Arm, which is older than those two, very nice product. Actually, they use 6 EMG sensors to capture electrical pulses from muscle. And you can see 3D printed using nylon PA12. They have a small, medium, and large. They have different magnetic covers, so you have so many options here. Weight, 0.75 pounds, which is 336 grams. A little lighter. And price, something between $12,000 to $20,000. And finally, TrueLimb from Unlimited Tomorrow. You can see it looks very natural, very beautiful product. Actually, they use 36 EMG sensors to capture those actually signals. And the nice thing about this product is they said it provides sense of touch by generating vibrations when arm makes contact with objects. So this is, I think, one of, maybe, I don't want to say first one, but you cannot see sensory feedback integrated with bionic arms. So I would say probably this is the first one. And again, 3D printed using nylon PA12. They can provide customized arms. So they can probably scan your body and they can create something specifically for you, which is nice. And weight, 1.5 pounds, which is close to 680 grams. And price, something close to $8,000. But it still is expensive. Okay, what was our solution? We were thinking, okay, we can have AI-based neuroprosthetics. So we can combine AI models with neuroscience and biomedical engineering to have a new solution for patients. So what does it mean, neuroprosthetics or neural actually prosthetics? It's a multidisciplinary field, as you can see, combination, integration of neuroscience and biomedical engineering. The main focus is to replace or modulate those parts of nervous systems that get disrupted, they have problem. Neural prosthetics or neuroprosthetic devices are devices that interface with nervous system. They can help users to restore or improve functionality of specific parts of body. So we were thinking we can add intelligence to a bionic arm, to a prosthetic arm, and have something related to brain signals. So this is our solution, AI-based neuroprosthetics. So we developed a mind-controlled prosthetic arm with a hybrid brain-computer interface. Okay, what does it mean? So why this solution? Or project, or I would say, or product has lower cost, completely 3D printed using different materials, and I will show you what type of materials we use. It has higher accuracy compared to EMG-based interfaces. There are some studies that they show that EEG-based interfaces are more robust and accurate than EMG-based systems, because imagine we have direct access to human brain signals. We can capture those signals and process them and use them to show one action. They are more robust, customizable. We have a 2D scanner and we can scan patients, or let's say human body, and then we can generate a mesh model, and then we can design something specifically for that user, and then we can print it. And non-invasive. We don't need any medical procedures or surgery. Completely non-invasive product. And here you can see one of our prototypes in the right side. Okay, I said brain-computer interface. Okay, what is brain-computer interface?
Would it be how the brain, like the interface, how the brain would interact with the computer, like how you take those signals and how you would output them?
Okay, perfect. Any other ideas? What is a brain-computer interface or brain-machine interface? BCI or BMI? So a brain-computer interface is a computer-based system or a software which can actually connect human brain with a computer in a simple word. So imagine direct communication between neurosignals from human brain and use them to control any external devices. It can be a computer, or it can be a mouse, it can be any robotic systems. So BCIs or brain-computer interfaces enable users to control or interact with different devices or applications. You can use a brain-computer interface for gaming. Imagine using your mind, you can play a game. Or you can use it to turn on the TV, use it to control any robotic system which has a control unit, because we need to control those parts, those devices. So as you can see here, brain-computer interface. So we have human brain, we can capture those signals, you can process them, let's say signal processing, and then in the right side, you can have any type of external devices, and then you can control them. Let's talk about some keywords. I said EEG signals. What is EEG signals? human brain can generate different types of signals in different mental states. So you can see we have 5 different types of EEG signals. When we say EEG or electroencephalography, it means a monitoring method to capture EEG signals from human brain in different states. So you can see in deep sleep, in dreaming, your brain can generate delta signals. As you can see, they have different frequencies from 0.5 hertz to 42 hertz. They have very small amplitude. I'm talking about microvolts, 50 to 100 microvolts, but they have different frequencies. Do you remember what is the frequency?
Of the one like you used to communicate? Was it the gamma or beta?
No, what's the signal frequency? It means how many times you can see a complete cycle of signal in 1 unit of time, in 1 second. So for example, in 1 second, we have 1 complete cycle, 1 hertz. When you have 2 of them in 1 second, we say 2 hertz. When you have 42 complete signals in 1 second, we say 42 hertz. So they have different frequencies, but all of them have very small amplitude. So in deep sleep and dreaming, you can see your brain can generate delta signals. You can see 0.5 to 3 hertz, low frequency. Drowsiness and deep meditation, you can see your brain can generate data signals between 3 to 8 hertz, higher frequency. Restful, physically and mentally relaxed. You can see, like this situation, relaxed. You can see your brain can generate alpha signals between 8 to 12, actually hertz. Alert, when you're active, your mind is active, attentive, you can see your brain can generate beta signals between 12 and 38 hertz. And finally, when you are completely active, when you are thinking to solve a problem, when you are learning, or when you do some actions completely active, you can see your brain can generate gamma signals between 38 to 42 hertz. So I imagine in this situation, your brain is something between maybe alpha to gamma. So when we say EEG signals, we are referring to these type of signals. So we need to capture human brain signals and process them. Let's talk about brain lobes, because we need to capture these signals from human brain. Human brain has 4 lobes in each side. So the first one is frontal lobe. It's located in front of your head. We have 2 of them. This lobe is responsible for cognitive function, for control thinking, for planning, organizing, solving problems, movements. So most of the time when you're active, these signals come from this lobe. We have parietal lobe. It's responsible for sensory information, to processing information like taste, touch, pressure, temperature, and pain. It's in the back side of the, after actually frontal lobe, as you can see right here. We have occipital lobe. As you can see, it's positioned right here in the back side of the skull. It's responsible for visual information processing, for image processing, let's say, from your eyes. And then we have a temporal lobe, which is responsible for memory formation, for language processing, and for emotional regulations. So we have 4 main actually brain lobes, and we can capture signals from different actually brain regions. Next one, we need a device to capture EEG signals. So we call it EEG headset or EEG cap. This one is one of the old actually EEG headsets that we use in our research lab, Emotive Epoch X. It has 14 electrodes. So it's a 14-channel EEG cap. It means at the same time you can capture 14 different signals from brain. And it uses wet electrode. It means they are actually saline-based electrode because you need to use something to have a better connection, better connectivity. And you can see this is one example of electrode positions. I will talk about these actually letters and numbers. Another EEG cap that we use is from OpenBCI. They are open source EEG brainwares that you can use to capture human brain signals. They use dried electrodes, so you don't need to use that actual liquid. And we have these two. One of them has 8 to 16 channels, and this one has 21 channels or 21 dried electrodes. They can capture high resolution EEG signals for us. So, because when you want to capture and process those signals, you need to have a high quality EEG signal. So it means you need to have a good actually EEG headset or EEG cap. These EEG caps are for research purposes. They are expensive, but they are just for research purposes. In actually medical settings, you can see we have, for example, 64 electrodes actually EEG caps. So they are more advanced EEG headsets. I just wanted to show you the electrode placement location. So you can see by default, you can move those electrodes. But by default, if you use 8 channel, it means if you use just 8 electrodes to capture signals. This is the location, FP1, FP2. It means frontal 1 and frontal 2. Or C3 or C4, it means central. We don't have central lobes, but when we refer to C3 and C4, as you can see here, so you can see the location of actually these electrodes. They are somewhere between, in the midline of the skull, in the left and right. And then P7, P8. So the first actually letter refers to brain lobes. T, temporal, for example. F, frontal, for example. And if you use 16 channels, by default, this is the location of those electrodes. You can be flexible, so you can change the position of those electrodes and capture signals from a specific human brain region. So each electrode has a letter which shows brain lobes. And then even numbers refer to those electrodes which are on the right side of the brain, and odd numbers refer to those electrodes which are positioned on the left side of the brain. So again, we have in each side we have 4 lobes. I would like to talk about different actually positioning systems. We have some international standards to place EEG electrodes. We have 10-10 or, for example, 10-20 systems. 10 and 20, these numbers refer to the actual distances between electrodes, between adjacent electrodes. For example, either 10% or 20% of the total front back or right-left distance of the skull. So here you can see in 10-10, we have more space and we can have more electrodes. In 10-20, we have more space between electrodes. more distance, it means we need to have lower number of electrodes. Okay, let's go back to our solution. So we talk about EEG signals, what is brain-computer interface, what is EEG cap. So we have everything that we want. We just need a user. We need one interface to capture EEG signals. So this is our solution. We developed a hybrid brain-computer interface. I call it HBCI, using multiple machine learning techniques. And we developed a brain-controlled prosthetic arm. So we have two different things. We have one robotic arm, and we have one interface, hardware and software. Our device can interact directly with EEG signals captured by those EEG headsets. And then we can actually process those signals and find any changes in brain waves when user thinks about a specific thing. And then we can convert those signals to action, to command, and then control the arm. Very simple. But it's not that simple. So this is our pipeline. So input. We use EEG caps to capture EEG signals from human brain. And then we use actually different types of denoising or enhancing techniques to, I would say, pre-processing, to make those signals ready for feature extraction and classification. And then in our actually interface, we use two machine learning or deep learning techniques, combination of CNN and RNN for feature extraction and for hybrid classification. In the middle of this interface, we have training phase, and I will talk about training later. And then after this, we process and classify those signals, and we can translate them to meaningful commands to control the arm. I try to add as much as technical information actually we can share with you, because because of intellectual properties, we cannot disclose all technical information of this project. So, but you can see, you can have a general overview of our work right here. At the core of our hybrid interface, we use a combination of two neural networks for feature extraction and for signal classification. By two techniques, we tried different models, and finally we decided to combine these two, and we received the best accuracy result. CNN, convolutional neural network, and RNN, recurrent neural networks. If you are familiar, they are very famous machine learning techniques. We use CNN to capture and deconstruct special patterns or special properties of brain signals, and we use RNN to capture temporal patterns of EEG signals, so two different patterns of the EEG signals. When we say a special pattern, it means we are talking about distribution of electrical potentials on the scalp. Again, when you think about something, when you do something, your brain can generate different types of signals, and those signals come from different brain lobes. We use CNN to find those signals which come from a specific brain regions when you're active, when you are thinking about doing something. So we use them, let's say, we use them for brain region localization, to localize, to find those specific brain regions that we need to focus. Most of the time, we need frontal lobes or parietal lobe signals. And why CNN? Because CNN is perfect for special pattern detection. Usually, if you're familiar with deep learning and machine learning, researchers use a CNN for image processing. And RNN, we use them to capture temporal pattern of EEG signals. What does it mean, temporal pattern? We are talking about sequence of changes in brain activity in both time domain and amplitude domain. So we need to actually extract those temporal features from EEG signals. And why RNN? Because they are perfect for temporal and sequential pattern detection. For example, researchers use RNN for speech recognition, for text recognition, when you have sequential data types. So here you can see our hybrid model. So we use a different number of layers in both CNN and RNN to enhance the accuracy of our interface. So we tried different number of neurons, we tried different inputs, outputs, and we tried combination of different AI models. And finally, we decided to combine these two. Let me show you the result first, and then I can talk about training. So here we can see the classification accuracy of our system. We tested this hybrid interface with a public data set. You can see it's available public EEG data set with 64 channels. It means you have access to 64 high quality EEG signals, and you can actually test your model. And also we decided to use one of those actually EEG caps to capture our own EEG data set. And we tested different actually deep learning models, and you can see the classification accuracy. And the best result in both public and our own recorded data set was combination of CNN and RNN. So that's why we decided to combine and use these two. This number is in a research lab. When you have a real user and when you want to use this interface in real world, numbers will be different. So imagine clean situation, no interface, no distraction, perfect situation, and you can see perfect number. But we compare them in a similar condition, in the same situation. I talk about training. What does it mean, training? For each user, we need to have a training session because your brain can generate different types of signals from my brain. So for each user, we have a one-time training session. We ask the user to think about a specific commands. For example, for that bionic arm, we have two simple states, open, close. We ask user to think about open multiple times, and we can capture EEG signals and find the right pattern. Same thing, we ask user to think about just close. Imagine close hand, close palm. Again, we can capture those signals. So we can create two models for open and close. And then we can create a profile for each user. Next time, when user thinks about same command in real time, we can capture those signals and then extract the features, classify them, and then compare them with those models we have in the profile and say, okay, they think about open or close, and then show the action. And this is just one-time session, but you know, when we want to calibrate the system, when we have a new user, we need to redo that training. And our data set is something like this. You can see we have different types of electrodes, and for each one, we have a number. So here you can see one example of our data set when the user thinks about open, or another data set when they think about close. This is our first generation arm, or first prototype. You can see it's, what do you think? It's not bad. So it's very robotics. Actually, we used 4 motors or 4 actuators in this design. As you can see, they are located right here. We didn't have enough space. We had to control 2 fingers with just 1 motor, and for the rest of them, 3 motors. So 4 actuators for 5 fingers. And we use a high quality, actually, microlinear actuators. They have linear movements. And we use a small Raspberry Pi Pico microcontroller to actually, it's our main control unit. And you can see some details. You can see, for example, fingers. And here you can see the 3D printed version. It's right here. Actually, I removed the upper part, so you can see we have just 4 actuators right here, completely 3D printed using PLA and actually tough PLA. So if you want to see it, thank you. And for our first generation arm, actually, we developed a pattern recognition-based brain-computer interface. And then we applied and received a grant from NIH, actually, which was distributed from Kinetic. And we worked to design and develop the new generation of the arm and a hybrid brain-computer interface to enhance the accuracy of our BCI. And this is our second generation arm. Okay, what do you think? It appears more natural. So you can see the difference between this one and the previous one. And we were able to actually change the design. And finally, we used 5 actuators. So you can see we have 4 of them, very similar to that old design. And then we added another one in the back side. So 5 motors for 5 fingers. So we are able to control fingers, operate them individually or together at the same time. And we switched to Raspberry Pi 4 single board computer. It's not a microcontroller, it's a microcomputer. It means you have a small computer here, so you have USB port, you have micro HDMI port, and you can see you just need to connect a keyboard and mouse, and then you can install operating system. You can install Windows, Linux-based operating system, for example, Ubuntu or Mac OS, and then you have a computer. Just connect your monitor and then you can use it. So we use this one as a main control unit of this actually design. And here you can see we have this arm with extension part. So we are thinking, because people can have different types of upper limb amputation. So we are thinking, okay, we can have an extension part and cover so many people in different situations. So you can see more details here. So we try to have very nice and natural, actually, hands. And this is our second generation arm with 5 actuators. And we can actually add this extension part. So we try to be innovative. So we have 3 parts. This is our complete arm. We have one extension here, and we can have another extension here to cover different situations. So completely 3D printed using PLA, PLA tough, and some ABS materials. And you can see 4 models right here, another one right here. I would say it's not that heavy, it's good, but we are going to switch to another material, and I will show you. And we have very nice movement, and you can see the arm. And here we have a battery and our main control unit. So we have a standalone system. It means you don't need to connect it to computer. We have our EEG cap. We can capture signals and send them wirelessly to this computer. And then for training, we prefer to connect it to a computer because we would like to see the signals when user thinks about different commands. And when system is trained, we don't need to have a computer. So we have our main control unit right here. Thank you. And we use a rotating buckle system. Have you seen something like this for shoelace? So we can actually make this part tighter for different people. So you can see the same thing. This is our arm, EEG-based brain-computer interface integrated with this product. We can use 8 to 16 EEG electrodes. Completely 3D printed, is customizable. Again, we can use a 3D scanner, and then we can have an engineered, customized arm. Weight, 1.83 pounds, 830 grams. It's a little heavy, but we are going to switch to another type of material to make it lighter. Did you notice this part? You can see those fingers. We use a soft and flexible material, TPU95. We tried different settings. We tried different type of flexible materials. And finally, this is our best result. So you can see completely soft, 3D printed. It's very thin, something around 0.5 to 0.6 millimeters. And do you know why we use this soft material to print this part? There's a space right here if you touch those fingers. So we can put something right here. So we tried different settings, printing temperature, bed temperature, thickness, density, and we tried different type of materials. And finally, we decided to go for TPU95A, which is this one. We are going to add sensory feedback to these fingers. Do you remember tooling? They have sense of touch. We are going to add sense of touch, sense of pressure and sense of temperature to this arm. So this is our future plan. So imagine you can have different sensors here. So when user actually grab something, so we can generate a signal and we can convert it to vibration, and they can feel they grab something. We can capture temperature, but we need to find a way to send it back to brain. So this is our future research projects. And also pressure, so we are able to adjust the pressure for different users. And we are going to have 3 different arms. First one, we are going to have a manual prosthetic arm, which will be very cost effective. For those patients, for those people who don't want to use any type of interfaces, they don't want to use EEG or EMG based interfaces. We are going, if you noticed, we have a small place for a switch. We are going to have a switch on that arm without any interfaces. So they can just press that switch and open fingers. Press it again, close fingers. Or maybe we can do it with a specific amount of time, or we can have a momentary switch, and when they press it and hold it, they can actually adjust how much they want to actually open the fingers. So it's a very simple mechanism. Second one, our current project, we are going to have EEG-based brain-controlled prosthetic arm, which is this project. And third one, we are going to have EMG-based arm as well. So we received a new grant, internal grant from NKU this year. And this year we are going to print a new arm with a new material and then combine it with EMG sensors. For some people, maybe it's easier to use EMG sensors. And I would like to build our own EMG-based device and compare it with our brain-computer interface. So we're going to have 2 types of arms. Here you can see Nathan, one of my research assistants. So he just thinks about open and close, and you can see the movements of the arm. He thinks about open and close. So this is unintentional, so there is no connection between hands. He just thinks, so he's trying to focus. And we had we had 3 TV interviews with different channels, so WCPO9, Spectrum News, and KET from PBS. And you can just watch one of them.
Only on WCPO 9 News right now, a helping hand for those who use a prosthetic. The future may just be in grasp in a classroom at Northern Kentucky University.
Amazing stuff happening there. Anchor Evan Millward's here with us to show us the research to make life a little easier. All right, how does this work?
To make this fist and open it again, I didn't push a button, flip a switch, even twitch a muscle.
I didn't.
I just thought about making a fist.
I'll be darned.
Bionic arms and hands that can move like this one cost tens of thousands of dollars. Some require surgery to implant sensors.
Actually, limb amputation.
Enter NKU Assistant Professor Mahdi Yazdanpour.
Our solution was to design and develop a hybrid brain-computer interface and a mind-controlled prosthetic arm.
He, another professor, and a couple of students have a National Institutes of Health grant to use this cap to capture electroencephalography, or EEG signals from the brain.
Different events in the brain cause different strengths of EEG signals.
This thing will eventually be more stylish.
Imagine you have a baseball cap, at the same time you have some small electrodes, and we can capture your EEG signals.
Those electrodes send the signals to a computer, and it turns them into code, which activates the actuators of this 3D printed arm.
I watched as a Terminator when I was a middle school student, so I'm actually feel like this is actually fascinating.
Assistant Professor of Data Science Young Tao has more altruistic aspirations than the Terminator, but it is a good comparison.
I feel like I'm actually doing something doing something like the Terminator, and we are creating some like a robot and can actually do some like smart stuff, like something like that.
Their goal is to build a better, a cheaper, a more natural bionic arm.
Our approach is completely non-invasive, so we don't need any medical procedures or any surgery.
It's just like you are controlling like your real arm.
And there's still plenty of work to do. Tao is focused on using artificial intelligence to make this work smarter.
If you're thinking about like open and close arm, the arms can like move real time, like very fast. Like it's just like you are controlling like your real arm.
Yazdanpour is working on a new grant to make this hand more sensitive.
We are going to add some sensors here to help people when they grab something, they touch something, we can generate a signal and convert it to vibration.
And so that would help you grip something better, or tell you that whatever the arm is touching is grabbing, it's hot or it's cold. Again, just working to make the existing technology better. They're working to get another NIH grant to jumpstart that part of the research next, guys.
Okay, let's skip this one. Our future plans. So we are currently working with Kentucky Commercialization Ventures, KCV, on patentability assessment and for commercialization of this product. At the same time, I'm working with two coaches from LaunchBlue. Again, they are trying to find the best commercialization path for this product. So this year, we are going to start human tests. So we are going to ask real end users, real patients to test this interface so we can actually enhance the accuracy of our BCI. We are going to add sensory feedback to the arm. We are going to design a customized EEG cap. Those EEG headsets or EEG caps are not very user-friendly, so we cannot ask a user to have something like that EEG cap. So we are thinking to just integrate a few electrodes into a smart, for example, a sport cap or hat, and it's easier to capture EEG signals. We are going to design and develop our own control board. We are going to develop EMG-based bionic arm, which is our project for this year. And then we are going to submit a proposal for NIH Camber, and we received the initial confirmation and they are interested in this project. So we are going to submit a new proposal for another grant. And then we are going to add sensory feedback. And let's talk about Neuralink. Have you heard about this company, Mr. Elon Musk? So it's a neurotechnology company, and they develop implantable brain-computer interfaces. They designed Link, a small coin, completely implantable, and you can use this interface to control electromechanical devices. It has 64 threads, and they are very thin, and actually you cannot use human hand to implant them. So they use this surgical robot to implant that actually Link, and you can see the needle is thinner than human hair. January 2024, they did first human test. And last month, this is the latest update. Progress is good. Patient can actually control or move a mouse around the screen by just thinking. So imagine you can have a brain-computer interface and you can control anything you want.
This is Pager. He's a 9-year-old macaque who had a Neuralink placed in each side of his brain about 6 weeks ago. If you look carefully, you can see that the fur on his head hasn't quite fully grown back yet. He's learned to interact with a computer for a tasty banana smoothie delivered through a straw. We can interact with the Neuralinks simply by pairing them to an iPhone, just as you might pair your phone to a Bluetooth speaker. The links record from more than 2,000 electrodes implanted in the regions of Page's motor cortex that coordinate hand and arm movements. Neurons in this region modulate their activity with intended hand movement. For example, some might become more active when he moves his hand up, and others when he moves it to the right. By recording from many neurons and feeding their activity into a decoder algorithm, we are able to predict Page's intended hand movements in real time. First, we calibrate the decoder by recording neural activity as Pager uses the joystick to move a cursor to targets presented on the screen. As he's playing this game, we are wirelessly streaming, in real time, firing rates from thousands of neurons to a computer. Using these data, we calibrate the decoder by mathematically modeling the relationship between patterns of neural activity and the different joystick movements they produce. After only a few minutes of calibration, we can use the output from the decoder to move the cursor instead of the joystick. Page still moves the joystick out of habit, but as you can see, it's unplugged. He's controlling the cursor entirely with decoded neural activity. Our goal is to enable a person with paralysis to use a computer or phone with their brain activity alone. Because they wouldn't be able to move a joystick, they would calibrate the decoder by imagining hand movements to targets. One of the things the Neuralinks allow Pager to do is to play his favorite video game, Pong. To control his paddle on the right side of the screen, Pager simply thinks about moving his hand up or down. We've removed the joystick altogether. Now that he's up to speed, let's increase the difficulty and see how well Pager can play with the Neuralink. As you can see, Pager is amazingly good at mind Pong. He's focused, and he's playing entirely of his own volition. It's not magic. The reason Neuralink works is because it's recording and decoding electrical signals from the brain.
Great game, Pager. And what better reward for a monkey than a banana?
We still have challenges spanning many fields of engineering.
So our main goal was to help people with upper limb amputation to control a bionic arm using their minds. But we are thinking we can use a brain-computer interface to control any devices. So we are thinking to bring this idea from research labs to enhance people's lives. And I forgot, one of our future plans is to switch to a new material. So do you remember I showed you Hero Arm and TrueLink, they use nylon PA12, this material. We are going to use the same material for our new MG-based interface. So I can show you this part later. Very detailed box, very nice material. And I think I'm done. I need to mention, actually, I had the privilege of mentoring 15 research students at NKU, and 5 of them from 2020 to 2024 actually were working on this project. And Dr. Yang Ta joined our research team last semester from College of Informatics, and he's expert in data science and data processing. And I'm happy to actually work with Dr. Yang Ta. And we are trying to work together to enhance the performance of the whole system. And thank you. And you can scan my virtual card, so you can find my information right here. So if you have any questions, feel free to ask or contact me.
When were the actuators small enough that you could incorporate them in your hand or into the hand? Did you need the computing part? Were the actuators already small enough, but you needed the micronization of the chip in order to do the hand, or was it the other way around?
So those actuators, as you can see, we use the same actuators that are in our old design. So we use same thing or new design.
Now, do you expect to have any more miniaturization of those actuators, that you could put more functionality into a hand?
I think we don't need to use a smaller one because we just need those actuators to move fingers. But we are thinking to have a smaller control board because you can see we have a large control board and we have a large battery right here. So we need to work to minimize the scale of hardware that we have right here. But I think we have right scale actuators here. We don't need something as smaller than this.
Thanks.
Thank you.
Mahdi, I have two questions. Number one is, right now the hand is, you can open and close it, right? But when you look at the human hand, it's much more complicated. You can do many more movements like this, right? If you want to touch things, if you want to hold a pencil, if you want to write something, or you want to open the fingers separately and stuff like that. Particularly when you drive around, you probably want to use your middle finger or something like that. So how are you working on that?
So we are thinking we can do something like here. Most of the bionic arms, they have just two simple movements, open and close. But you can switch to different movements. Okay, let me find here arm and you can see. Okay, can you see they have a small button right here? So you can press this button and then you can switch to different modes. Just 2 fingers, for example, 3 fingers or 5 fingers. So we are able to have different types of codes in our control units. And then we can have something like this. Okay, just press switch to have these 2 fingers. Press another one to have 3 fingers. Press another time to move all of them. But it's really challenging if you want to control just 1 finger using your mind. It will be a very complicated brain-computer interface.
So we are not there yet, but it's...
No, we are not there. But, and you can see, for example, in a Link project, the user can just move the cursor.
Yes. Yeah.
You know, it's really hard to do complicated movements because, you know, when you think about something, EEG signals are very similar. So it's really hard to find the right pattern when you think about specific commands.
Yeah, and that brings me to my next question. I think you worked on this already. What about if you have somebody who is paralyzed, right, and when he sits in a wheelchair? Can you use the brain function to control the legs? Can you animate the legs? I mean, you don't have artificial legs, you use the same legs you have, right? Because you have the muscles still, you need to train the muscles again, but could you do that?
It would be possible to use brain-computer interface to, again, control any electromechanical devices, any robotic system. On the paper, yes, it should be possible to control a robotic leg, for example. But, you know, again, it's easier to control fingers. And we were thinking it will be actually people need to move hands, move fingers. So we were thinking, okay, it has more priority to develop EEG-based bionic arm. But technically, yes, it should be possible to control something like that. But we need to try.
Our folks online can answer or ask questions through the question and answer portal. But we did have one question from the online audience, and that is asking sort of what kind of price range that these would cost to make. You made a point about some of the others being very expensive. I wonder if you could talk a little bit about that.
The arm that we printed in our research lab, you know, the situation will be different when you want to commercialize a product. But our price is something between $2,000 or $3,000 in our lab. Might be cheaper, but, you know, I'm considering different actually situations. We need to purchase actually different parts. This arm has something around 34, 35 different 3D printed parts, plus more than, I think, 30 small parts, so nuts, screws. So we need to purchase those parts. We need to actually purchase control board and battery. So the current price would be something between $2,000 to $3,000, not more than that. But I'm sure we can save cost, and in commercialization setting, maybe the price is different.
But that's not how you go to the market, right? I mean, when you go on the market, you want to still make some money for the company. So it had,
when you go on the market, you still need to you want to make a profit, right? So you have to get usually a factor of 2 or 3 or something like that, correct?
Yes.
So then you would be, if this costs you $3,000, then you would charge $9,000 to the customer.
It's not 3, so it's, it's 2,000 something, but we are going to have our own control board. We are going to switch to a new material. So I'm sure we can, our final product can be in the same range, 2,000 something, but yes, we need to consider some hidden fees in commercialization section. It will be more than this, but again, hopefully we can have something less than $8,000. And again, the main difference, EEG based, those are EMG based.
So similar to that question, one of the questions we have online is how long it takes to make one. So you talked about it being 3D printed, but you also talked about it being very customizable so that someone could have one that's built specifically for them. So what kind of production time does that take? Or I appreciate that you're not in mass production, but if someone was to, if you were to make one today for me tomorrow, what would that look like?
If you want to design something from scratch and 3D print it and assemble it, it takes around 2 weeks for us to finish everything.
All right. Well, thank you so much for your time this evening and for all of you for joining us and our folks at home. We appreciate your time, and we will post the video on our website, and we will send you an email when that is done. But we appreciate your time tonight, and thank you so much for joining us for 6 at 6.
Thank you.